So, welcome, dear participants. In this session, we have with us Dr. Bibhu Sahoo from IIT Kharagpur. He will be delivering a talk on the topic of noise issues in analog design. I will hand over this session to him so that he can deliver his talk. Thank you.
Thank you. Today's topic is noise issues in analog design, and in this topic, I'll be covering. We'll go into a little bit about a brief introduction. It will be mostly be a circuit perspective treatment, and not mostly. It is a circuit perspective treatment, and we'll be discussing about different noise sources in the components like the transistors, resistors, and all. And then we'll go into something called quantization noise. Discuss the impact of that noise on the overall performance of some systems like analog to digital converter. Okay, so how you need to design. So how does the thermal noise, the quantization noise, and any other noise, like there is something called jitter, clock jitter in a sample system, and all those things, how do they affect the overall performance of the converter? Okay. So, introduction to circuit noise. Electrical noise is current or voltage signal that is unwanted in an electrical circuit. Noise is not deterministic but is random. So when we have something random, then we do resort to something called statistical analysis. Okay. Instantaneous amplitude of noise is not predictable. So we go for something called average power of the noise, which is mostly predictable in in all the systems. Most of the sources of noise in circuits exhibit constant average power. Now keep in mind, for a periodic signal, average power is given by this expression where Vt is the voltage across the resistor. Okay, and Vt is a periodic voltage source. To simplify calculations in case of random sources, in case of noise, we make RL equal to 1 and treat the noise source xt as a voltage, and therefore we say that P average across a 1 ohm resistor is x squared integral of this, and is expressed as volt squared rather than watts. So we express the noise as volt square rather than watts. The RMS value of the noise is RMS voltage for noise is square root of this average power. Typically, we don't deal with noise in time domain, although time domain analysis can be done where we do correlation by autocorrelation and cross correlation, but mostly frequency domain analysis is preferred. And in order to do a frequency domain analysis, we look at something called a power spectral density, means what is the power per unit frequency or per hertz, and it has the dimensions of volt squared per hertz rather than watt per hertz. Although it is called power spectral density, we call it as volt square per hertz. So you can see that this is how the power spectral density looks like. Common type of power spectral density is white spectrum. So white means white color has all frequencies. So similarly, white spectrum means it has all the frequency components, and it is all the frequency components having equal power. So that's called a white power spectrum spectral density. Now, whenever we have a noise source and we have an analog circuit, so that means, and the analog circuit takes in an input, gives you an output. So when it takes an input, that is a desired signal, and gives you an output, it does some processing on it. Similarly, the noise that is there in the circuit will also be processed by that circuit. So we have to there is a transfer function from the output, from the input to the output, or from the noise source to the output. There is a transfer function. Okay, and we know in a linear time invariant system, LTI system, if the transfer function is h of s, okay, and there is a noise source whose power spectral density is given by Sx of f, then the output power spectral density is given by the Sy of f is equal to Sx of f times the h of f square, which is the magnitude of the transfer function. Okay, So this is a well-known formula, and this is what is going to be used whenever we try to analyze any transfer function. So we will analyze one today, an integrator, and we'll figure out what is the transfer function, and then find out what is the overall noise power at the output. We'll find out first the power spectral density, and then integrate that power spectral density over a frequency band to get the overall noise power. So once we obtain the power spectral density, then you integrate it between a band F1 and F2 and find out the total noise in that band of frequency. Typically, the noise is usually, we can analyze noise by considering two-sided spectrum or a single-sided spectrum. They mean the same thing as far as analysis, as far as the total noise contribution is concerned. So when we consider two-sided spectrum, then the total power in a frequency band F1 and F2 would involve integrating in minus F2 to F1 and F1 to F2. Okay. And if I want to represent the same noise as a single-sided power spectral density, then all I do is I double it and do it like this. So the height at each point is twice the height at each of these points. So similarly, if I have a two-sided white spectrum with eta over 2 as the power for each frequency, then a one-sided white spectrum would look something like this. These are all, you guys, all of you know very well all these things. Now, when we analyze a random process, random source or random process, we use something called a probability density function. Okay. Now, probability density function tells you if we take various noise samples and find out how often each sample comes, we can construct a plot showing distribution of each sample. So now, the simplest thing which I am sure all of you do in when you grade your students is if you have 100 students, you give them marks, and then you get the histogram of that. You plot, okay, 10 to 20, how many are there? 20 to 30, how many are there? That means you are actually, in a way, you are plotting that histogram when normalized, which then it is called a probability density function. Normalized with the total number of students, it is called the probability density function. So a probability density function can also be considered as histogram if it has the number of times it occurs. Okay, so how often each sample comes is number of times a sample occurs. Okay, the distribution of x of t is defined as px of x dx, which is the probability of x lying in this small infinitesimal band. Typical, most of the if I take many independent random processes of arbitrary PDFs and I add them up, then the central limit theorem says that the overall distribution that I end up with has a Gaussian distribution with a mean m and the variance sigma. So this is the PDF of a Gaussian distributed thing. So typically, the noise sources that are available that exist, most of them have Gaussian distribution. The thermal noise, the flicker noise, they have Gaussian distribution. Gaussian distribution means the amplitude distribution. What is the value of how many times a certain amplitude of noise occurs? That is the distribution. Yeah, power spectral density is how much is the power in each frequency. They're two different things. Now, when we add two noise sources, so if I have a noise source x1 and x2, the total power is given by this, which is nothing sum of these two square. Now, if I do an expansion of the sum, then it becomes the power of the first noise source, P average 1, then the second noise source, which is P average 2, and finally their power, this is the cross power between the two, which is nothing but the cross correlation between the two random noises. Okay. If x1 and x2t are generated by independent sources, means let's say there are two resistors, okay, then they do not know how much each one is generating. So now when I take the cross correlation between them, it turns out to be 0, and these sources are said to be uncorrelated sources. Otherwise, they are correlated sources. Signal to noise ratio is an important parameter that we also discussed yesterday. The SNR is the signal power divided by the total noise power, where P noise is the integral of the power spectral density from minus infinity to plus infinity. Okay, so this is the total noise power is the integral from minus infinity to plus infinity. So noise analysis procedure. Identify the sources of noise and write down the spectrum of each. Okay. Find the transfer function from each noise source to the output as if the source were a deterministic signal. This is an important thing. When we find out the transfer function from each noise source to the output, we treat as if it is a deterministic signal. So we treat that noise as a voltage source and find the output voltage divided by the noise voltage, and that is the transfer function. And then we find, and using the principle of superposition, because it's a linear system. Utilize the theorem Sy of x equal to this to calculate the output noise spectrum contributed by each of the noise sources. So there, let's say there are 10 noise sources, x1, x2, x10. And now x1 to output, there is a transfer function h1. X2 to output, there is a transfer function h2. And x10 to output, there is a transfer function h of 10. Then the output, the power spectral density, due to x1 is s of x1, so it will be sy1, s of x1, h1 of f square. Similarly, for each of the sources, s10, sy10 equal to sx of 10, h of 10, f. So this is for each of the, and when we are doing this, we set the input signal to 0. Add all the output spectra, paying attention to correlated and uncorrelated noise sources. Now, if the noise sources are correlated, then you have to add them in voltages. If the noise sources are uncorrelated, then you add them in power. So the above procedure gives the output noise spectrum, total output noise spectrum due to all the noise sources. If we have 10 noise sources, the total output noise spectrum is obtained. Then we integrate from minus infinity to plus infinity to yield the total output noise, because P noise is the integral of this. Two popular kinds of circuit noise are thermal noise and flicker noise, and but there are other noises also, but these are the two most important ones that also occur in CMOS circuits. Okay, now resistor noise, random motion of electrons causes fluctuations in the voltage measured across the conductor, and the resistor noise is modeled as a particular resistor, noisy resistor is modeled as a noiseless resistor, and the noise source in series with it. And this noise source has a power spectral density 4 kTr, one-sided power spectral density of 4 kTr. If it is two-sided, you put it as 2 kTr, which goes from minus infinity to plus infinity. If it is 4 kTr, it goes from 0 to infinity. The MOSFET thermal noise is actually a drain current noise, okay, and that is given by 4 kT gamma GM, where GM is the transconductance, and this occurs when the MOSFET is in saturation. Gamma is 2/3 for long channel devices and 1 for short channel devices. Okay, the gate resistance also gives you a thermal noise, so which I am not showing here, which I am ignoring, because usually that is not that dominant in most of the analog circuits that we build, because we take care of the gate resistance by making sure that we have multiple fingers and we have multipliers in the design. Okay, so the drain current noise becomes a dominant noise source. Okay, now let's see, if I have a resistor and I have a capacitor, what is the overall output noise? So now this resistor has a noise source, is denoted like this. We find the output to input transfer function as it's a low pass transfer function. Therefore, S out of F is equal to the power spectral density of this noise source times the magnitude square of this one, the transfer function. And when we integrate this from minus infinity, the total output power is kT over C, which is independent of the value of the resistor. And this makes sense, because if I increase the value of the resistance, then the bandwidth reduces. So it is going to filter out more high frequency noise. If I reduce the value of the resistance, it is going to have a wider bandwidth. So therefore, it is not going to filter that much, but the overall area under the curve is going to be independent of the value of the resistance, which is therefore turns out to be kT by C. So in a system, if I need to reduce the noise, the solution is increase the capacitance. Okay, now if I increase the capacitance, you pay a power penalty. Okay, and that is not very good. So there is a trade-off of power versus noise. The second dominant source of noise in MOSFET is the flicker noise, which is due to the dangling bonds between the silicon dioxide and the silicon crystal. Charges get trapped between there, give rise to extra energy states as charge carriers move at the interface. Some are, they should be interface. Some are randomly trapped and later released, resulting in, so when this charge is moving under in the crystal, that time some of the charge gets trapped and later released, and these are released randomly. So therefore, it leads to something called flicker noise. The flicker noise is more modeled as a 1/f noise. The power spectral density of this is as a 1/f. That means at DC the flicker noise is infinity. Okay, and the reason we call it at DC, we can certainly not measure it, because if I'm trying to find how much is a flicker noise at DC, I have to wait infinite time. Okay, so therefore, but it becomes as we approach DC, the power of the flicker noise becomes very, very large. Now, there is something called a flicker noise corner frequency, which is the flicker noise has a 1/f characteristic, okay, and the thermal noise has a flat characteristic. They would finally intersect at a point, and that point is called the flicker noise corner. So at the flicker noise corner, the 1/f noise power spectral density is equal to the thermal noise power spectral density, and therefore the flicker noise corner can be given by this expression. Okay, so now if I need to reduce the flicker noise corner, especially for sensor applications, okay, that means I need to reduce also the flicker noise, then I have to increase the area of the transistor. If the area of the transistor is more, then my flicker noise power is less. Okay, and therefore and also in PMOS, the factor K turns out to be smaller. So we actually either go for PMOS devices for sensor applications where we have very low bandwidth signal sensor or biological signal processing. We go for very low, we go for either PMOS input devices, or very large devices are used so that the flicker noise power is less. Okay. So without going into the basics of this thing, I'll just give some results in terms of noise in differential pairs. These are all taken from the textbook. So if I have a resistor loaded differential pair, then there will be drain current noise, okay, of M1 and M2. The resistor also will provide noise. Okay. Now the resistor noise has a power spectral density 4 kT/RD. Okay. Now keep in mind, this noise and this noise are uncorrelated noise sources. Okay. So therefore the power at the output will add up. So we have a factor of 2 over here. Similarly, this noise and this noise are uncorrelated, and therefore these two noise sources are adding up in power over here. Now you can see that the total output noise power is given by this. But when we are trying to analyze the circuit, the total output noise power has very little meaning. What we want is the total input referred noise power. Okay, because if I compare to total output noise power, it is meaningless, because if the circuit has more gain, it is the total output noise power is going to be more. But at the same time, the circuit signal will also be amplified significantly. So the input referred noise is nothing but the output noise divided by the gain square, and therefore the input referred noise is given by this expression over here. Okay, so now in order to reduce the input referred noise, you have to increase the transconductance of the input devices, okay, as given by this expression. Okay, and you increase the transconductance by increasing the current, so you burn more power to get lower noise. Similarly, if I want to reduce the noise due to this one, I can increase the resistance, input resistance, but increasing the resistance compromises the swing at the output, compromises the bandwidth also. So, so there is a trade-off between power, speed, and SNR. Okay, SNR translates to the total noise. Now, the tail current noise is a correlated noise. So if this noise, there is some noise due to the tail current source, this noise, if it equally splits up, finally appears here as common mode noise, and when we take the differential output, they cancel out. So this is an example of correlated noise. Okay. Now, what about the 1 over f noise? 1 over f noise is given by this expression. This is the 1 over f noise at the input here, and the factor 2 comes because we have two devices, and these two are uncorrelated. Each of them, the 1 over f noise is modeled as a gate noise in series with the gate of the transistor. So the total noise is the thermal noise and the 1 over f noise. Now, if we have a current source loaded amplifier, then there will be drain current noise due to M3 and M4. There will be drain current noise due to M1 and M2. Now, M1 and M2 drain current noise, when I divide it by the gain, so this term is same as this term over here. Okay. Now, but this term over here will now there will be a ratio of GM3 by GM1 square. So you can see that GM square comes in 1 over RD instead of 1 over RD. We have GM3 over here. Okay. So GM3, and then this is the flicker noise component due to these two. This one, and the flicker noise due to this gets amplified by the GM of this device and get attenuated by the gain of this circuit. So therefore, GM3 by GM1 square comes in over here. Okay, because the noise, flicker noise from here goes to the output by GM3 times the output impedance, and then we divide it by GM1 times the output impedance. So the output impedance gets cancelled out over here. So we have a ratio of the square of the transconductances. Now this is for one of the transistors, so the total input referred noise will be twice of that because we have two of them which are uncorrelated. So 8 kT due to the thermal noise and this due to the flicker noise. So the bottom line is, the amplifying transistor GM has to be maximized to minimize the input referred noise. So the amplifying transistor M1, GM1, okay, GM1. The current source load transconductance has to be minimized to minimize the total input referred noise. And of course, the device sizes have to be increased if I have to make sure that my flicker noise is as small as possible. Okay. I think this should have been twice here. I missed out a factor 2 here because there is a factor 2 already here. So there is a typo over here. I'll correct this. Now there is something concept called noise bandwidth. So noise bandwidth corresponds to, if I have the total integrated output noise, what is the total, what is the equivalent bandwidth if I have a white power spectral density noise of a certain power. Okay. So, and if I have a first order, like if I have a first order case like this circuit, okay, then the equivalent noise bandwidth is pi over 2 times the pole frequency. Okay. And the pole frequency is 1 over RC. Okay. And so that is the noise bandwidth. Now, in case of a telescopic op-amp, okay, the noise sources are drain current noises of all of them are present at the output. So now GM12, this is the input device noise current, GM12, 4 kT, and the factor 2 comes because M1 and M2. Now this is the thermal noise due to this gets amplified to the output by a factor GM7 times the output impedance, and then we divide it by the gain from the gain of this device. So GM12 square will come in over here, and this factor is due to the fact that we have 7 and 8, two of them uncorrelated noise sources. The flicker noise due to M1 and M2 show up over here, okay, and the flicker noise due to M7 and M8 are given by this expression. The noise due to M5, M6, M3, and M4 do not come into the picture, okay, or they are severely attenuated. Now, I hope all of you know already that why this noise, these noises, these do not contribute to the noise, because when we try to find the noise, the drain current noise due to M3, how it shows up at the output and divided by the gain of this circuit. Now, this M3 device, the noise current, is degenerated by the output impedance of M1. Similarly, the drain current noise of this M5 is degenerated by the output impedance of M7. So therefore, the effective transconductance for the noise current to get to the output has severely reduced because of the good amount of degeneration that is there, and therefore the cascode devices hardly contribute. They even contribute less than 1% or 2% to the total noise. So therefore, we can, for all practical purposes, the cascode devices can be considered as if they are noiseless, because their noise do not contribute to the total input referred noise. Okay. So any questions on this? I'll move on to something called sample thermal noise.
Sir, 1 minute, one doubt.
Yes.
Sir, in the previous slide,
Yes.
yeah, sir, before this, the slide before this.
Yes.
So here also the GM4 does not come into picture.
GM4 comes into the picture. Yes. So so here you can see that I have written GM1
Yeah.
and then multiplied that by 2 here, right? To consider M1 and M2.
Okay. GM3 and GM4. Okay, fine. So twice of GM3. Yeah.
Yes, twice of GM3. So 8 is given over here.
Okay.
So this whole thing is multiplied by a factor of 2 to account for M1 and M2 and M3 and M4.
Okay. Yeah. Thank you, sir.
Thank you. Any other questions on this basic? Yes.
Sir, what is the difference between input referred noise and output referred noise?
So suppose I have two amplifiers, okay, A1 and A2, okay. Now, if A1 has a gain of 1, okay, and A2 has a gain of 10, there are two amplifiers, A1 and A2. A1 has a gain of 1 and A2 has a gain of 10. Okay. Then let's say the output noise of both of them are same. Total noise, integrated noise of the power spectral density is, let us say some number X, output noise. So which one is a better circuit?
A1 with gain equal to 1.
How is it a better circuit? So let's try to analyze it. Okay. So if I have okay, so let me see if I can 1 second. Okay, so A1 gives you noise, output noise is X. A2 gives you output noise, same output noise. Okay, A1 and A2 are giving, but this has a gain of 10 and this has a gain of 1. Now, when at the input of A1 I applied 1 millivolt, what do I get at the output? I'll get 1 millivolt. And 1 millivolt I can find the corresponding power if it is a sine wave. So let's say square it. This is not correct, but I'm squaring it to say that, let's say that is the power at the output. Then divided by the noise power X. Okay. Now here I apply the same 1 millivolt, and then I'll get 10 millivolts at the output. Correct?
Yes.
And I square this to get the power. Although this is squaring the voltage is not the power. Just keep in mind, this is just an approximation here. If it's a sine wave, you have to find the power as square by 2, or V peak to peak, RMS value you have to find, and then square of that RMS. You have to integrate it. And then I divide it by X. Now, which one has better SNR?
Second.
A2.
Second one. A2.
SNR2 will be greater than SNR1. Correct?
Yes, sir.
But both of them have the same output noise. So that means looking at the output noise does not tell you whether one circuit is better than the other. So now what is the best way? So that means I'll now let us compare the same thing with by dividing this by 1, the input referred noise is X and input referred noise is X by 10. Then I don't even have to go to the SNR computation and clearly say that this is better than this. Does it make sense?
Yes, sir.
Okay.
Okay, sir. Thank you.
Any other questions?
Sir, we assume that transconductance GM3, GM4 all are equal. So mismatching of the transistor will not contribute to the noise.
Yes. So the mismatch between the transistors would lead to slightly different noises. So here, if you see, it will be 4 kT by 3 GM1, and then it will be plus 4 kT by 2 by 3 GM2, right? So you can
Yes.
just plug in the value this thing. So let's say GM1 is there and GM2 equal to 1.01 GM1,
Yeah.
right? So for all practical purposes, it is the same, right?
Oh, yes. Yes.
Okay. So now let's get into some other concept called alias sample noise. Now, when we sample a signal, okay, what happens is that when I do an impulse sampling of a signal, then what happens? The spectrum of the signal shifts to the left and to the right infinitely. Okay, but impulse sampling is not possible in reality, but let us assume that that is happening. But if we go for a sample and hold, then then the signal does get shifted left and right, but after shifting it gets attenuated by the sync pulse. Okay, so therefore let us consider we are taking a sampled signal. That means I have a circuit whose output noise power spectral density when it is looking like this blue line. Now I'm sampling. Now keep in mind what is a sampled circuit. So it is a switch. Okay, so I'm taking this V in and there is a switch resistance and I'm closing this on and off periodically. Okay, and I'm sampling onto this capacitor C. So when we have this scenario, what is happening here is that now when the switch is closed, this circuit will filter out the noise, and let's say the blue line is this thing. Now keep in mind, a sampled system is such that if I'm sampling at a certain rate Fs, then this RC time constant will be much smaller. Okay, so that the signal perfectly gets sampled onto this capacitor. Okay, so that means the bandwidth of this circuit, this RC circuit, the bandwidth is much larger than the sample rate. Sample rate is Fs and the bandwidth of the signal will be much larger. I hope this is clear to everyone, right? So therefore, the for all practical purposes, I am sampling a signal whose spectrum looks like this blue line, and I'm sampling at a rate Fs. When I sample something at a rate Fs, everything outside Fs by 2 gets aliased into Fs. So this part of the spectrum will come over here. This part of the spectrum will come over here. This part of the spectrum will come over here. And this part of the spectrum will come and sit over here. So the total area, the area under this blue curve and the area under the red curve is exactly the same. Okay, so the bottom line is when I have a sampled system, then the area under the non-sampled system, RC, if I don't have this switch but just a V in and RC, the area under this curve, and when I have the sampled system, the area under that will always be the same as from but the power spectral density from 0 to Fs by 2 has increased significantly. Okay, so so basically the bottom line is you can work this out. Tau is the time constant, which is R times C. Fs is the sample rate. Okay, now F3 dB is nothing but F3 dB is 1 by, so tau is related to the 3 dB frequency. So 1 by 2 pi this thing. So basically the power spectral density in 0 to Fs by 2 increases by this factor in a sampled system. So therefore sampled systems are said to be little more noisy than a continuous time. Therefore switched capacitor delta sigma are not preferred, but continuous time delta sigma are preferred because they do not have this aliasing of the noise. Now let's try to analyze this. 1 by F3 dB is the settling time of the system. The settling time of the system. This is a 3 dB. That is the settling time of the system. 1 by 2 Fs is the settling period for a two-phase clock. Now, in order for proper sampling to happen, this relation should be satisfied. Okay, so that I can sample a signal to n bit accuracy. If I have to sample a signal to n bit accuracy, then I have to satisfy this relationship. So you can work this out by doing e to the power minus t over tau, how the voltage gets there, and I have to sample to within the full scale divided by 2 to the power of n, and then you will come up with this expression. Therefore, PSD is increased by at least n plus 1 ln2. This increase in PSD is 1 plus ln2, n plus 1 ln2. If n equal to 10 bits, the PSD is increased by 7.6 or 8.8 dB. The power spectral density increases by 7.6 or 8.8 dB in the 0 to Fs by 2. That is what it is. This is an inherent disadvantage of sample data compared to continuous time systems, but noise is reduced. But if I go for oversampling, then the noise, then this is reduced by oversampling. By whatever amount I oversample, that is, the noise is reduced by that. Now let us try to find out, analyze the noise in a switched capacitor integrator. Okay, so the switched capacitor integrator, this is a parasitic insensitive switched capacitor integrator. That means it is insensitive to the parasitics at the input of the op-amp. These slides have been taken from Richard Schreier's notes. So I'll put a citation to that when I'm sharing the slides. So therefore, the two-phase, the switched capacitor in phase 1, it samples the signal. And in phase 2, whatever charge is stored on this is integrated onto this capacitor. And therefore, we call it as the integrating phase. Phase 1 is the sampling phase and phase 2 is the integrating phase. Now, in phase 1, let us draw the RC equivalent circuit. RC equivalent circuit has this resistance, capacitance is there, and this resistance. Okay, so therefore, there are two resistors and two noise sources. So we can say that these two resistors are in series. So therefore, two I's are on, and the noise voltages, these are uncorrelated. So it will be root 2 VR on. Okay. So what we can see is that now the total sampled noise on this after integration is given by KT over C1. This is straightforward. We have already done this. Okay. So time constant of RC filter is this, and therefore you end up with this. Now in the integrating phase, the equivalent circuit has this resistance, capacitor, this resistance. So this R on 1 and then R on 2 and this capacitor. Now there will be switch noise and there will be op-amp noise. Now keep in mind, this op-amp can be, let's say, what we just looked at, this op-amp. Now, if I ignore the flicker noise component, then the op-amp noise will be given by this. Okay. Now, if I take 2 by 3 GM1 common, what do I end up with? It will be 1 plus GM3 by GM1. And that we call it as the noise factor. That is what is called the noise factor over here. And therefore, so the equivalent noise of the op-amp is given by this expression. This is exactly this over here. 16 by 3 KT GM1. So this is exactly this one, and NF equal to 1 plus GM3 over GM1. Now, if I this noise on this and this is finally getting onto this, integrated onto this capacitor C2. And if we work in order to analyze that, we'll use the equivalent circuit of the op amp and try to find the transfer function. And once we find the transfer function, we can find out the total noise integrated onto the capacitor due to the op amp on C1 and on C1 due to the switch is given by these two expressions. Okay, so total noise power both switches on integrating phase is this. So we can find out what is the total output noise. Find whatever is there on C1 and C2, C1 finally gets onto the C2 as well. So that's why we just find this one out. Okay, now total noise on C1 on both phases is therefore given by this expression. Okay, so this is the minimum value of this. Now what is X? X is equal to twice R on times GM1. R on is the switch on resistance. GM1 is the transconductance of a single stage amplifier. So if I make sure that if this tends to infinity, if X tends to infinity, that means GM1 times R on is very, very large. Okay, then I can achieve the theoretical minimum, which is twice KT by C1. What was assumed to be the total noise was actually the least possible noise. If I do not consider anything, twice KT by C1 is the noise sampled on this one. Keep in mind here, twice KT by C1 if it's a differential operation. But that is actually the minimum noise, but there is some additional noise. Now, if I plot this for noise factor of 1.5, what is one noise factor 1? And this ratio is 0.5. Okay, so if it's this thing, you can clearly see that as I vary this X, which is twice R on GM1, then the op amp noise keeps on reducing and the switch noise keeps on increasing. Okay, now the total noise will be something else depending on, so as X keeps on increasing, then the total noise is finally going to have reduce and approach this one if X tends to infinity. Okay, so is this any questions on this aspect on the sampled noise? There is this is based on the 2005 Transactions on Circuits and Systems 2 paper by Richard Schreier and Gebert Emisch. So this has been summarized quickly in these few slides. So I'll cite that paper. I forgot to put that. So all this analysis is based off of that. Okay. So having discussed, so till now we have discussed noise sources, op amp noises, which is standard. Then we talked about sample noise. And how does a sample noise come onto an integrator? An integrator is one of the key building blocks in a lot of systems. Okay, GMC filters or in Delta Sigma ADCs and all. Okay, any questions on sample noise and noise in a switched capacitor integrator? Yes, okay. If there are no questions, I'll move on to the next aspect, which is quantization noise. Okay. Okay. Now, when we quantize a signal, yes, I'll share the paper. It's you can search on the internet. So let me quickly share that on this thing. Yes. So the title of the paper is I'm sharing that right now on the chat. Title of the paper is this. Authors authors are Richard Schreier, then Silva, Stinsgaard, and Eberseetevish. And this is in IEEE transactions on Circuits and Systems 1, November 2005. Okay. Okay. So now we'll discuss about quantization noise. So now there are two kinds of quantizers. Okay. One is called a mid-thread quantizer. Okay. So here a quantizer has a quantization step of Q. So when the input changes, X is the input and the X dash is the output. When the input changes by a quantization step X, then the output changes. So in a mid-thread quantizer, it changes over here. So that means it doesn't change at the zero crossing. And a mid-rise quantizer changes at the zero crossing. And this is how the mid-rise quantizer looks like. Okay. Both of them have an average slope. Average slope of 1. Typically, all ADCs and DACs implement a mid-thread quantizer. All ADCs and DACs actually implement this one. Okay, so this is of much more relevance. Now, we also looked at the probability density function earlier. So, suppose I have a random process, and at any particular time I get these values of the random process. Okay, so there are multiple of them, and I take these values and I plot how many times does this value come, how many times does this value come, and all. So area of each bar equals to the probability of signal being within the quantum box at time t1. So this is how the relative frequency is going to look like, frequency of this thing. And when I normalize, if I make this quantum box infinitesimally small, we get something called the PDF. And the interesting thing about the PDF is that the integral from minus infinity to plus infinity is equal to 1, because the probability cannot exceed the total. This is equal to the total probability of the signal, and therefore probability cannot exceed 1. So that's why it is equal to 1. Okay. So now why are we doing this? Because we will be finding the SNR by two means. We will be finding the SNR by finding the signal power by integrating a signal over a time, and the noise power also by in time domain. We can also find the signal and noise power using something called the PDF as well, probability density function, because there are two ways of finding the powers, and we'll show that. Probabilities are areas under the PDF. When transforming a variable y equal to fx, we transform the PDF by preserving the area like this, where the absolute values are taken as the changes can be positive or negative, but the probability has to be positive. Now, hence, probability of y equal to fx is a function like y equal to sine omega t. That means x, if I consider t as a variable, then y sine omega t is a function. Okay, is the y. P of y is px divided by dy by dx. So this is nothing that is coming from this expression, where the derivative is obtained at x equal to n f inverse y, and fx should be a one-to-one invertible function. This is a constraint on this thing to work. Okay, if the function is many to one, then its inverse will have many solutions. If it is not one-to-one, then the inverse will have many solutions, and then we have, for each of those solutions, we have to find the probability of y. Okay, now let's see how to calculate the PDF of a signal x equal to f of t, right? So this is a method to find the PDF. So PDF of y from the PDF of x. Okay, now how do I find a PDF of x? From f of t, which is sampled uniformly with a period of t. Okay, that means the independent variable is the time and there is uniform sampling, the probability of that is 1 over t. Okay, the function x equal to f of t acts to transform the above density from 1 over t time to 1 over x. Okay, therefore p of x equal to p of t divided by dx by dt, and derivative is evaluated at this value. So let's take an example. Sine wave x equal to sine t. I have removed the frequency and everything, assuming the 2 pi f equal to 1. Okay, dx by dt, this term dx by dt is defined at t equal to sine inverse of x. The inverse sine is defined in this range uniquely. Okay, only in this range it is defined uniquely. P of t is uniform within this within this, and P of t equal to 1 over pi. The uniformity time is uniformly distributed between minus pi by 2 to plus pi by 2. Therefore, you can prove that P of x equal to 1 divided by pi square root of 1 minus x square. Okay, so P of t is 1 over pi. Okay, and dx by dt will be square root of 1 over 1 minus x square. So this is the PDF of a sine wave. And interestingly, if you can you can actually plot, if I have a y equal to sine r sine omega t, then our PDF of a sine wave is going to look like this. Means the value of the sine wave, you will see more values at its peaks. So you can see, because the slope of the signal is minimum at that point, so you will get maximum number of values. And when the signal is going through zero crossing, you will have minimum number of hits. So this is how the PDF of a sine wave going to look like. You can try it for yourself, generate a sine wave in MATLAB, take the histogram of that and plot it, and you will see, you will get a curve like this. Okay. Now, if we'll now compute the quantization noise power based on this analysis. Now, applying a ramp or sawtooth waveform to the quantizer results in the quantization error waveform given by this. Okay, the error profile can be written like this. You can work this out. It will be written like delta t. T is the sampling period. T is the time for every time. Error profile is going to increase. It will have this step size. EQT is centered around 0, but we have approximated to simplify estimation of its power. The quantization noise power is the area under this, and this turns out to be delta square by 12. This is obtained by taking a ramp input, integrating this total thing, okay, and finding out that it is delta square by 12. Now, if I take a sine wave, and as I said, you can see that when I quantize the sine wave, for these values, it is getting large lot of, it is staying constant for a lot of these values, but here it is changing very quickly. And this makes sense, which means that our PDF is going, there will be more number of values coming in here. Okay. Now, if I take the difference between this blue curve and the red curve, the dotted line, then this is the quantization noise profile. Okay. The quantization noise profile has sawtooth waveform at the zero crossing and has a sinusoidal kind of a waveform at its peaks and the valleys. So the quantization noise is sawtooth around the zero crossing, but has bell-shaped characteristic around the peak and valley. Okay. Now, if I have the signal is given by this, I can write this, a sampled signal can be written in this format. Okay. Now, if I choose Fin by Fs as if the input frequency is chosen, which if the ratio of the input frequency to the sample rate is co-prime, then you will see that the histogram has uniform distribution. Okay, the histogram has uniform distribution when the ratio of the input to this one is co-prime. However, if the ratio is not co-prime, then your quantization noise profile is going to be not uniform anymore. And if it is not uniform anymore, then we cannot approximate the quantization noise power by delta square by 12. Okay. So therefore, when you are reading any papers related to the quantization or data converters, and you're looking at the SNR and the FFT spectrum, make sure that they have chosen an Fin by Fs which is not easily divisible. If it is divisible, that means they will get a very, very high value of SNR, which is incorrect and which is not the right thing to do. Okay. Now, here we are saying that this is purely due to quantization noise, right? But then there will be thermal noise, so the PDF will have some amount of uniformity here, but there will be a lot of values around this which are fixed. Okay. Now, if they are not co-prime, then you are always sampling the same values from period to period. Therefore, the sampled signal is repetitive and has only a few distinct values. So this means that the quantizer generates only a few distinct values of EQT, implies not a uniform distribution. So you can write a MATLAB code exactly like this. Okay, choose Fin by this and vary n from 0 to 10,000. Okay, quantize this signal. You will get a PDF like this. Run a choose Fin by Fs as this. You will get a PDF like this. And you can clearly see that this is not uniform, and therefore the SNR estimation in this case will be much, much higher than the SNR estimation over here. Okay. So to avoid repetitive nature of the sampled values and to generate uniform distribution of the quantization noise, the repetition rate of the samples should be increased significantly. Choose Fin by Fs equal to P by Q, where P and Q are integers and are co-prime. The repetition rate of the samples will be Q. Make Q as large as possible. A good rule of thumb is Q should be greater than 2 to the power of n. If n is the resolution of the ADC, make sure that you choose Q much greater than 2 to the power of n. Usually I choose it at least 4 times 2 to the power of n. If Fin by Fs equal, then the repetition rate is 10 samples. That is, every 10 samples the values repeat. Keep in mind here P equal to 100, Q equal, they are not co-prime. If Fin by Fs equal to this, then the repetition rate is 1000. That is, every 1000 samples the values repeat. Okay, you can try this in MATLAB and see for yourself how they repeat and how the PDF of the quantization noise is no more uniform, and you get a very optimistic estimate in this scenario of the SNR. Okay. Now, we have said that we will compute the quantization of the SNR can also be computed by something called using the PDF. Okay, so for an arbitrary signal waveform that spans from -V to V, the signal power is computed like this. So x squared t is the signal, and this is the PDF. P of x is the PDF. P of x is the PDF. This is how you compute the signal power. Okay. Now, in case of sine wave, what will happen? A squared sine squared omega t. PDF is 1 by square root of this thing. Okay. The noise power. So this is how you compute the signal power, and the noise power we have computed as delta square by 12 because it is uniformly distributed. So therefore, my SNR signal is uniformly distributed between this SNR equal to 6.02 n. If it is an n-bit quantizer, means if I have a signal which is uniformly distributed, not a sine wave, then SNR is 6.02 n. If a signal is a sine wave, then probability of x is this, SNR equal to 6.02 1.76. And yesterday somebody asked if it is random, something else. If the signal is Gaussian, as in case of OFDM, SNR is given by 6.02. Oh, sorry, this should be 6.02. Sorry, let me just correct that. 6.02 n minus 7.27. So Gaussian distribution P of x is given by, we had given the Gaussian distributed PDF earlier over here. This is a PDF. So plug in that PDF over here. So you can compute the signal power by integrating in time domain, or by compute the signal power by this expression. Okay, you can choose any of those. Now the question is, if I have a Gaussian distributed in case of OFDM, okay, the SNR is given by this. Now you can see that versus sine wave versus this, there is a 9 dB OFDM signal is 9 dB worse. Anybody knows why this is 9 dB worse? Have you ever come across these expressions, these three expressions? Okay, so basically, bottom line is sine wave is easier to quantify. That's why we choose. So when we talk about this, usually when we talk only quantization noise, then it is called SQNR. Okay, and if it is not quantization noise, there is other noise sources, then it is called SNR. Okay, so since we are talking about signal to quantization noise ratio, so this can be technically called as SQNR, and some people also call it as SNR. Okay. Now we'll repeat the derivation. We'll repeat the derivation of this quantization noise from a deterministic perspective of a sine wave. So if I have n bits, there are 2 to the power of n levels. Signal amplitude is A, that means A sine omega t. Quantization step is, full scale is A, so quantization step is this, A divided by 2 to the power n. The quantization error therefore lies between this. Now this quantization noise is uniform. We have seen that it is indeed uniform when I apply a sine wave. It is almost uniform. Okay, and the mean squared value is QS squared by 12. That we have also seen. And keep in mind the signal power can be obtained by either this way or by integrating the sine squared omega t dt, the function of t. Okay. Now, so A can be therefore, see, QS is this, so A can be written like this. The RMS value of a sine wave with peak amplitude A is given by this. So A is 2 to the power n of QS, and therefore the SNR is the signal power divided by this thing, and we get the same expression of 6.02 n plus 1.76 dB, which was also written here. And this is obtained by doing A squared sine squared omega t, P of x, d of x. Okay. Now, dynamic range of a system is equal to the SNR of the system measured over a bandwidth equal to half the sampling frequency. This is another term that is also people use in dynamic range. Okay. Now, quantization noise density per bandwidth. Now, this is the quantization. Now, delta square over 12, which is QS square by 12, is the quantization noise. Now, this quantization noise power is spread over Fs by 2. So the quantization noise density per unit bandwidth is given by this expression. The signal to noise ratio density SNR as a function of frequency is therefore given by this. Okay, so signal power is this. The density, the quantization noise density is given by this. Therefore, SNR of a system up to Fsig is given by this expression. So if I do not integrate up to Fs by 2, then I will get, if I integrate to a lesser value, then I will get more and more SNR. I'll get roughly 3 dB improvement for every halving the bandwidth. Okay, so this is what it says, that that means if I do more averaging, I will get more and more SNR. Okay, now having talked about quantization, so we have talked about thermal noise, we have talked about flicker noise, we have talked about how sampling for thermal noise leads to aliasing. Then we talked about quantization noise and how to compute the power. Now we'll talk about when we are doing a sampling and the sampling clock is not very clean. There is noise in the clock. Okay, so ideally I should be sampling uniformly, means the clock's period should be uniform. But in reality, the clock edges are non-uniform because of thermal noise. Whoever is generating the clock, that is. So instead of sampling at a particular t, I sample at t plus delta t, resulting in an error that I am sampling of value delta a. Now, how does this error in the sampling degrades the SNR of a sampled system? So If the sampling instant changes from t to t plus delta t, we call it that as the sampling time uncertainty. Then the amplitude variation is from a to a plus delta a. Okay, this variation delta a should be less than qs so as to not affect the SNR of a converter. If it is less than the quantization step, we are fine. If the input being quantized is this, we obtain the sampling time uncertainty delta t as given by this. You can take the derivative and you get this expression. Okay. Now, if the ADC has n-bit resolution, this delta A should be less than the full scale, because this is V sine omega t. The full scale of this is twice V, and if it is n bits, it is 2 to the power n. So this should be less than this. In order to find this bound, so that means delta t should be less given by this. That means this is the maximum amount of error in the clock that we can tolerate. If I have an error more than this due to any noise sources in the clock, then I will degrade the SNR. Okay. Now let us quantify by how much does the SNR degrade now. If if we exceed this, or if there is some amount of jitter related to this. Slope of a sinusoid is maximum at zero crossing and thus results in maximum error at zero crossing. Okay. The SNDR degradation due to sampling clock uncertainty or clock jitter. Okay. Error due to clock jitter is delta A is given by this. Okay. So delta A is from here, delta A, V omega cos omega t, omega equal to 2 pi Fn. Okay. V delta t, that is equal to, if you multiply this is your error in the sampling instant, which is given by this curve here. We have an error of delta A. Now, if V equal to 2 to the power of n minus 1 of Qs, because Qs is 2V divided by 2 to the power n, so therefore V can be written like this. Qs is the LSB. So delta A is given by this expression. We just substitute V in this with this expression over here. The error power is nothing but this error square is given by this, and the average power is integrated over the whole period 0 to 2 pi. This is the error power of the delta A. Now we know that cos squared phi 0 to is half, so the average error power is actually given by this expression here. Okay, so therefore the total error, total power, noise power is the quantization noise power plus the average power due to the thermal noise of the clock. Okay, therefore the total power can be given by this expression, which is the quantization noise power plus another factor. Okay, 1 plus kj square, where kj is given by this. So you can find out kj from here. Okay, square root of this. Okay, therefore the resulting SNR degradation is SNR ideal n divided by n plus nj, which is equal to 1 by 1 plus kj. Okay, so this is the degradation in SNR where due to the sampling time uncertainty, and the sampling time uncertainty happens due to the clock edges not being perfect, and the clock edges are not perfect because of thermal noise, flicker noise, and other noise sources in the circuit. Now, if that is the case, how do we tell, okay, whoever is designing the PLL and you have to buy a ADC and you have to buy a clock source, how will you decide the specification of the clock source? Or how will you tell the other designer what should be the specification of the clock source? So we will discuss this. Let's take a 2-3 minute break and we'll resume after that. Is that okay? Before we take a break, I'm okay taking some questions. Any questions?
Sir, which book you are referring for all these equations?
I think these ones are, some of them, I think it's compiled from various theses. Then Rudy Vandy Plash has a book. Okay, so it's compilation from various different theses and all.
Yeah, okay, thanks.
Okay, there is David Klein's thesis, Yun Chio's thesis, Thomas Cho's thesis. These are the theses that were written in the 90s. Stephen Lewis's thesis and all.
Okay.
Okay.
Thank you, sir.
Any other questions? Okay, we'll resume at 1 o'clock sharp. Okay, any questions? So there is a question on gain of the quantizer for an n bit, how to obtain a gain quantizer, n bit quantizer gain. So when you have a quantizer, if it's an n bit system, it is much easier to compute than when it is a 1 bit quantizer. 1 bit quantizer can have any arbitrary gain. So different techniques are followed there. But if it is an n bit quantizer, you can always get the slope of the input output characteristic and get the quantizer gain. Okay. So any other questions? Okay, so now let us see, if I have to design an ADC with a certain SNR. Okay, the goal is what should be the jitter that we can tolerate to achieve that SNR. So let us so that you can now go and tell the guy who is building the PLL and generating the clock, or you can go to the market and look at the data sheet of the clock generator and say, yeah, this clock generator makes sense for me. Okay. So if the desired SNR is X dB, then what we say is that let us say that the jitter limited SNR is X plus 10 dB. So what does it mean? That means that what is jitter limited SNR? Jitter limited SNR is the signal power divided by the jitter power, delta A square power, delta A average square. So this is the jitter power, error due to the jitter, okay, noise due to the jitter. This is the noise due to the jitter. This is the signal power because we have applied a signal of value a v sine omega t. So v squared by 2 is the signal power. So the jitter limited SNR is given by this expression. Am I clear with this? So therefore, now v equal to qs 2 to the power n minus 1. So the SNR jitter limited. Now what is the SNR jitter limited? Is x plus 10 dB. So SNR jitter limited is therefore given by this expression, and by solving this we get the value of the amount of jitter that I can tolerate in the system. Now let us say if x equal to, now what does this depend on? The amount of jitter that I can tolerate does not depend on the sample rate. It is interesting that it is independent of the sample rate. You do not see the sample rate. It is dependent on the desired SNR that you want from the system and the input frequency, that maximum input frequency that you are trying to digitize. Now, suppose I want to make sure, I want to find out how much jitter can I tolerate if I have to sample a signal whose bandwidth is 1 gigahertz. That means I have to digitize a signal from DC to 1 gigahertz. And I have to digitize that to 12-bit resolution. Okay, 12-bit resolution corresponds to 74 dB. If I have to digitize a signal to 12-bit resolution, means x equal to 74 dB, then the amount of jitter that I can tolerate, if I have to digitize a signal from DC to 1 gigahertz, then I will plug in 10 to the power minus 74 plus 10 by 20 divided by 2 pi times 1 gigahertz. Okay, so this is the jitter limited, this is the amount of jitter. So if I have to use such a system, I have to go to the market and get the specific appropriate clock source, or I have to tell the PLL designer to appropriately design the PLL with that much amount of jitter. Okay, any questions on this? This is the design guideline. So this will be the, if I have to design what is the amount of jitter or the noise that I can handle in the clock source so that I can faithfully digitize that signal. Okay. Now, so basically, effective number of bits is measured as SNDR, where DR means the distortion is also there because the circuits are non-linear. So noise plus distortion minus 1.76. Now, as I said, the SNR of a system is 10 log of P sig divided by the quantization noise power and the thermal noise power. And this thermal noise power will include the power of the op-amp noise, the switch noise, the jitter noise, and any other noise in the system. Okay, so this is the overall SNR expression of any ADC, or for that matter a DAC as well. Okay. Now, we will do some analysis on how to size the capacitors for a sample system so that I can minimize the noise. Okay. Signal to noise ratio of an ADC, we have already seen, is the signal power divided by the quantization noise power, which is Qn, plus the thermal noise power. Now keep in mind, we said that this thermal noise power would include the jitter power as well, which we just obtained. The jitter power is given by this. Okay. And so P sig is the signal power. If the peak to if the signal full scale is V peak to peak, then it is the signal power is given by this. That means I'm applying a signal whose value is given P peak to peak is denoted as P dash P by 2 sine 2 pi ft. Quantization noise is delta square by 12, where delta is equal to V peak to peak divided by 2 to the power n for an n bit ADC. Okay. And NT is equal to the thermal noise power of the ADC. Now SNR of the semiconductor limited by thermal noise of switches and by the op-amp noise sources. Switch thermal noise can be minimized by using large capacitors. We have seen because it is the KT by C noise that comes into the picture. The thermal noise of the switches is given by KT by C. The op-amp thermal noise can be minimized by burning more and more current. So let's see what is the limit that we can achieve right now. Okay. It is costly in terms of power, area, and to make input thermal noise smaller than the quantization noise for ADC resolutions greater than 10 bits. Okay. So what turns out is that for 11 bit, 12 bit, 13, 14, 15, 16 bit high resolution ADCs, the thermal noise seems to be more dominating than the quantization noise. Now, how do we, if that is the case, that means for Nyquist rate ADCs, where I'm integrating all the way to Fs by 2, the noise, we are mostly thermal noise limited if we are trying to realize something greater than equal to 10 bits. Okay. So let's take an example. If the full scale of the ADC is 1 volt and we have an 11 bit ADC, the quantization noise power is given by this thing, which is 141 microvolt RMS. If I find this value, this is the square of this. If thermal noise voltage NT is same as quantization noise power, then the SNR takes a 3 dB hit. Does this make sense? So let's look at it. If Qn equal NT equal to Qn, then this becomes twice 10 log of 2 is 3 dB. So therefore the SNR drops by 3 dB. Okay. If SNR has to take a 1 dB hit, then NT has to be Qn by 10. The thermal noise should be 1/10 of the quantization noise. Size of the capacitor required to achieve this for 11-bit system is 2 picofarads, which is reasonably can be realized in CMOS process. For a 12-bit system, the capacitor required would be 2 picofarad. For a 16-bit system, the capacitor required would be 2 nanofarads. And all these are based on the fact our thermal noise is purely KT by C. We have not considered op-amp noise. We have not considered all the other noise sources as we have seen in this factor. I want to go back to that integrator thing where we have this, besides this KT by C, we have this additional factor that comes in. Okay. If I consider this, so these are not being considered when we are coming up with these capacitor values. Okay, when we are doing this, so ignoring other noise, thermal noise is only modeled, then the SNR, if given by this, then we can do if I have a full swing of 2 volts, means my ADC full scale is 2 volts over here, then we can safely build, I would say, 12-bit systems. So this magenta is 12-bit systems, okay, with roughly 10 picofarads of cap, which we can realize in CMOS. But if I have a 1 volt, and certainly I cannot achieve 14 and 16 bits because the size of the caps approach nanofarads, which we cannot realize on chip. Okay. Now, if I have a full swing of 1 volt, you can clearly see that we cannot achieve more than 10 bits. Okay. With reasonable capacitor sizes. So that is what the conclusion is, that if I want to realize something more than 10-bit system, and this is natural in case, not only in case of ADC design, In fact, for any when we are trying to build a variable gain amplifier or a filter, that filter finally we go for DSP. So that filter output will be digitized by the ADC. Now the filter will add thermal noise. So that thermal noise will also add to the overall thermal noise to the whole receiver chain. So so if I have a full scale, if I reduce the supply voltage, then most of the designs become thermal noise limited. Now, how do you overcome thermal noise limited designs? Then how do we receive a GPS signal which is embedded in the noise? The beauty of the noise that we have, both thermal noise and flicker noise, is they are zero mean. So we can average it out. That means we do some kind of low pass filtering. We filter out the noise and achieve like 12-bit, 14-bit, 16-bit, and in fact up to 24-bit performance. But you will see that 24-bit ADCs will have very low bandwidths. There will be few kilohertz ADCs. Okay, so since their bandwidth is very small, you can do a lot of filtering, which is nothing but averaging, and get back the resolution that you want. Am I clear with this slide? This is an important thing, how noise affects the overall performance of the ADC, of any analog system. Any questions on this? Okay. Now I'll go back to the thermal noise analysis, to that same optimization problem that we started off yesterday. Okay. We'll get to that, and I'll share an Excel sheet how we are going to do an optimization based on that. Okay. Now we know exactly the pipeline ADC looks realized with multiple stages, and each stage resolving fewer number of bits, and output of each stage is amplified and given to the next stage for further digitization. Okay. Now each stage contributes some thermal noise. Okay. Now the question is, if each stage is contributing certain amount of thermal noise, what is the distribution of the number of bits that each stage should resolve? Keep in mind, the number of bits that each stage resolves manifests as the equivalent amount of gain that each stage gives as well. Please keep that in mind. Okay. So what is the optimal distribution of the bits in each stage, or how should the gains in each stage be appropriately given? They are both the same thing. If n1 plus 1 bits, here 2 to the power n1, n2 2 to the power n2. So that means how should I distribute the number of bits on each stage to achieve a p-bit resolution ADC? Means how should I distribute the gains of each stage so that I minimize the total noise? So that is the problem statement. We minimize the total noise or maximize the SNR. Okay. Now, if I consider, let us say, now what will happen? The noise of this stage, which is showing up at the output, will be divided by the gain of this stage. So therefore, the noise of this stage will be divided by the gain of the first stage. The noise of the second stage will be divided by the product of the gains of the previous two stages, and so on and so forth. Now let us say we are considering that the noise is purely KT by C. We are not considering jitter or anything and all those things. Jitter will only show up at the input stage. It won't show up at the later stages. Let us consider only thermal noise, KT by C noise. Op-amp noise is also not ignored. Now each of those noise sources, you can say that the total thermal noise, when I have a cascade of n stages, is given by this expression. Now the goal is to find out G1, G2, Gn, so that the overall power consumption is as small as possible and SNR is maximized. Okay, SNR is maximized. Okay. Now, if C1 equal to C2, if I say that all these stages have the same capacitance, then the back-end stages, that means these values will progressively reduce It will be a geometric series with these values tending towards 0, the later stages. The back-end stages contribute very little noise, and therefore we are wasting power, because each stage we have to burn a certain amount of power to drive that capacitance, okay, because it's a GMC. But suppose we scale the capacitance of the later stages by the gain that we provide in each stage, then each stage contributes equal noise to the output, and this can lead to reduction in power. Okay, so now let us say all stages consume the same power. Power per stage is the same. There are n stages. Then noise per stage is like this, because the later stage contribute very little noise because they are attenuated by the gain, product of the gains. Now, if all stages contribute the same amount of noise, then the power per stage exponentially drops. So now these are two extreme cases of scaling for noise and power. In one case, noise is attenuated significantly, power is wasted. In another case, noise is decently large, but the power is significantly. So optimum capacitor scaling lies approximately midway between these two extremes. This is taken from David Klein's thesis, which is 1995 thesis. Okay, so therefore, when we have to, so there is an optimal strategy. So this optimal strategy was developed by Yun Chiu in 2004 in his paper, and he has shown how how should we scale every stage. And what it turns out is that there is an optimal scaling factor of for high-speed designs. The optimal scaling factor will be of capacitance is somewhere between probably 30 or something. So this is the tapering factor. X is 1, is what is a 1 to 1.25 is the tapering factor, and the power is minimum at this point. This is y-axis is the normalized power. Okay, but if I have for a low speed design, I will operate at close to a tapering factor of x of 1.5, which is the scaling. X equal to 1 scaling exactly by the stage gain. Okay, so so the capacitor scaling factor is 2 to the power of mx, because m is the stage resolution. So because mx, this is the 2 to the power of m is the gain that we provide, number of bits we resolve. Okay, now x is a factor by which I'm going to provide the gain so that I can get minimum power. Now that depends on whether I'm designing for a low speed system or for a high speed system. This x will be either 1.5 or will be 1.2 or something like that. Okay, so this is the optimal strategy for scaling for power. Okay, now lot of the sample systems do not have a sample and hold amplifier, and since 2003-4 they have stopped using sample and hold amplifiers in the front end of any sample system for digitization, because the sample and hold provides a gain of unity gain, and therefore the noise contribution of that is significantly large. We can see that these two, this is the first stage, later stages contribute less noise, but the sample and hold and these contribute. Now, in order to make sure that our thermal noise is 1/10, as we said here, thermal noise should be 1/10 of the quantization noise. We have to burn a significant amount of power in the sample and hold amplifier. And it turns out that the sample and hold amplifier can burn up to 1/3 of the total ADC power. So in order to overcome that, people avoid completely the sample and hold and go for a SHA-less architecture, which has its own challenges. Okay, now having said that, now I want to now move on to, as I said, we'll go through a simple exercise, okay, on how to, how on a pipeline ADC, what should be the strategy, what should be the gain distribution and everything, so that we can optimize the total power. Okay, so before we go into that Excel sheet, which I'll share also, any questions so far? So there is a question that somebody wants something about sigma delta ADCs, right? So that will be quite a bit of, I have to digress quite a bit. So which aspect of sigma delta ADCs are you talking about?
So the noise analysis itself, sir.
So which noise? Quantization noise?
A
Which gets changed?
quantization noise.
So the,
Since
I'm sorry?
since we also include the oversampling factor, no, sir, for the calculations.
Right.
So
So
does it affect the quantization part?
yeah, it does affect the quantization noise, right? So keep in mind that if you consider, so if this is the spectrum, okay, and this is fs by 2, my if I have no noise shaping, then my quantization noise will be uniformly spread. So it will have a uniform power spectral density. Now, if the input signal, if I pass that, if I filter out one third, so let's say this is fs by 6. That means I'm filtering out 2/3. Then my SNR is going to significantly improve, because these quantization noise is completely gone, and that is given by this expression that that I had given earlier. It improves by this. So if my f sig here, so let's say, so this is fs by 2, and let's say I go to fs by 8. So this is equal to f sig. Okay, so that means this is equal to f sig equal to fs by 8. So 10 log of 8. So how much is 10 log of 8?
$30. Close to 10.
So how much is that?
Around 9.
10 log of 8. Okay, now so that means how much averaging I have, and therefore an OSR of, how much is the OSR of 8, right? OSR of 8. Now if I have oversampling, OSR stands for oversampling ratio. If the quantization noise has a white PDF, okay, then, and I filter out anything above fs by 8, okay, then I get 9 dB improvement. Okay, if I filter out anything above, so this is OSR equal to 8. If OSR equal to 4, how much improvement do I get? 6 dB. And if OSR equal to 2, how much improvement do we get? 3 dB. And this is equal to 0.5 bit. Okay, because each bit is 6 dB. Now, so what does it, so therefore, if I have the quantization noise, now if I just purely quantize the signal, I have a white spectrum. Okay, uniform PDF. not wide spectrum, uniform PDF of this thing, which is a wide spectrum. Okay. Now, if there is a shaping, if I shape this quantization noise, and let us say I shape using a first order differentiator, okay. Oh, sorry, I made a mistake here. So how do I? Okay, so let's cut this out. 1 minus Z inverse. This system, if the quantization noise is passed through a filter which is 1 minus Z inverse, let us see where are the zeros of 1 minus Z inverse. The zero of 1 minus Z inverse is at 1. 1 is DC. Z equal to 1 means DC. So that means this is a high pass filter. Okay. So this is shaped by this. If that is happening, then for every doubling of the bandwidth, okay, we will get 9 dB improvement. 9 dB improvement. That means 2 will give us 9 dB here. 4 will give us 18 dB improvement here. Okay, and 8 will give us 27 dB improvement. Okay, so this is what the noise shaping does. Now, if I noise shape with 1 minus Z, this is called first order noise shaping. Order quantization noise shaping. If I do with 1 minus Z to the power of minus 1 square, this is called second order noise shaping. And this would give us 2.5, which is 15 dB for every doubling of the band, the oversampling ratio, OSR. Okay, so this is what you can easily figure it out through, you can pass this 1 minus Z inverse square and the quantization noise, which is uniform. If you pass it that through this transfer function and you integrate from 0 to Fs by Fs by what OSR, you will clearly see that you are getting this much of improvement. We use the same expression of this. This thing, the quantization noise passed through 1 minus Z inverse square or 1 minus Z inverse, depending on what, and then integrate that from the desired frequency with whatever is the desired frequency, which is Fs divided by OSR. Okay, so that is what gives you the overall performance, overall SNR improvement in case of a delta sigma ADC. Okay. Now, in a delta sigma ADC, typically it is depends on what kind of delta sigma. If it is a discrete time delta sigma ADC rather than a continuous time, in a discrete time, sometimes it is thermal noise dominated because the input thermal noise is not shaped because it is out of the loop, feedback loop. But any other thermal noise is shaped and there is an improvement. But in a continuous time delta sigma, you are limited by mostly by the jitter, clock jitter based thermal noise, clock jitter based noise, as well as the quantization noise. What is AIC 2022? I did not understand that. Okay. Any other questions? Okay, so if none, so let me go to the, can you, you can see my screen, right? Okay. So here I'm showing some, so if you have, I'll share my PPT. So this is what I want to show you how the overall power scales. So the overall power is computed over here. Okay. So I will give you all the expressions. Those expressions are from these slides. From these are from these slides have been used to obtain those expressions. So let me explain what is. So if the full scale of the ADC is between plus minus 0.75, okay, the number of the bits is 12 bits, and therefore the LSB is actually, you can see there's twice of this divided by 2 to the power of this. This is the LSB. Then quantization noise is this square divided by 12. This is the Boltzmann's constant. This is the temperature. KT is given here. And let us say I'm going to do the scaling that we just discussed over here. This scaling by a factor of 2. Okay, that is the scaling that we are doing. Now, since we are doing a scaling by a factor of 2, we have a feedback factor of 0.5 because that is what we saw yesterday, that this gives a gain of 2 and as a feedback factor of half. Okay, so we are trying to, and the skewing time is, I have given 500 picoseconds. Settling time is 1.7 nanoseconds. So this is the value of pi. Overdrive voltage is 150 millivolts, and it's a 200 megahertz system. Okay, little less than little 7.5, 1.7. Yeah. So I'm giving 1.7. So it is like a 50 megahertz circuit. Okay. Now, this is the value of the sampling capacitors on each stage. So I'm trying to realize a 12-bit system. So I'll have 9 1.1 bit stages, 1.5 bit to be precise, and finally a 3-bit flash. Okay. Now the sampling capacitor, I'm scaling them by a factor of 2. So 1 picofarad in the first stage, 500 femto, 250 femto, 125 femto, and from 5th stage onwards, I'm keeping 62.5 femto all, because I cannot scale these, because these, if I keep on scaling, they'll become very, very small and it is difficult to realize on chip. Okay. Now this reference voltage is, we saw yesterday that the power, the SNR, is maximum when peak to peak swing is equal to supply voltage. Right? Now, if I have a supply voltage of 1.5 and I swing plus minus 0.75, then I achieve full 1. This ratio becomes 1. That is how I choose VREF. Okay. Now, gain of each stage is 2, because that is the gain of this 1.5 bit stage. Okay. So, sorry, I'm jumping around because I want to correlate that to the gain of this is 2. Okay. Now the sampled noise is twice, I'll keep it here, twice of, you can see the factor of 2 coming in here, KT times C. This is the sampled noise. Why twice? Because it's a differential circuit. Okay. Now input referred noise, this is the first stage, so the input referred noise is the same, but this is the second stage. It is scaled by a factor of 4. So you can see that this is this square. So which is this expression here, second stage gain square. Okay, and all of them are like that. Now let us see. Now when I resolve 10 bits, 1 bit in the first stage, I will relax the settling requirement by 1 bit. Okay, so therefore, since I am realizing a 12-bit system, my settling requirement in the first in the input side should be 13 bits, LSB by 2. So for the next stage, it will be 12 bits. So that is what is exactly, it is 12. Next stage is 11, 10, 9, 8, 7, 6, 5, 4. Okay, for all the stages, the op-amp settling. Now, if I need to settle to 12 bits, how many time constants do I need? N plus 1, ln 2. So you can see this is 12, 11 plus 1, because I have resolved 1 bit, 12, n plus 1, 12. So F12 times ln 2, that is the number of time constants. How much gain do I need? I need a gain of 2 to the power of 12. That is independent of how many bits I resolve here. Next stage, 2048. These are the op-amp gains that I need. Okay. Now, what is the first pole location? How do I come up with the first pole location? So now let's go back to the slide and see what is the expression that we use to obtain the first pole location. First pole location is, I have the settling time. Okay, so here it is given, so number of time constants. Okay, H12, the gain, because I have the feedback factor, so this will be G12. So wait a second, so here is the so 1 plus 2F6. So it is A divided by 1 plus A beta, which is this term over here. And then this will be 2 pi F5, which is the settling time that I am giving here. Okay. So this is the location of the first pole of the amplifier. Now, if this is the gain and this is the first pole, how many decades does it need to hit the unity gain frequency? You need 3.5 decades, resulting in the unity gain frequency of 1.2 gigahertz. Okay. Now the load capacitance CL is the second stage in series with the first stage, this thing. So this is the load capacitance. The second pole, we know that the second pole has to be 5 times the unity gain bandwidth. So we have made it 5 times the unity gain bandwidth, so 6.1 gigahertz. And therefore, we can solve for GM2 by looking at is GM2 equal to, we know the load capacitance, we know the second pole, so we can solve for GM2. And the omega P1 is known. So we say that the DC gain of the second stage is 10, DC gain of the first stage is this. So therefore, we can find out R2, GM1, R1, CC. And once we obtain that, we can then obtain the ID1 and ID2, the first stage and second stage currents. Okay. So all these numbers are obtained from this expression here. And then finally, I can compute the power. Now, if I change the capacitance here to 2 picofarads, then you can see that automatically your power number will change. Okay, so this is a method that this is in an Excel file. You can code this and find out, which one is the lowest power design. And here I have, what is the effect, what is the total SNR that we obtain? So you can see that I have said that the Fin max is 25 megahertz, jitter is this much, delta T. Jitter noise voltage I have obtained, reference noise voltage, op-amp noise, buffer noise, and therefore the resultant SNR is signal power divided by all these noise sources plus the quantization noise. Okay, so this will be the thermal noise limited system, because we have built a 12-bit system, but our SNR is less than 74 dB. We are losing that because our other noise sources are all dominant more than the quantization noise. Okay, so with this, I think I'll stop. I'll share the 2 sets of slides as well as this Excel file so that you can play around, and if you have any doubts, you can ping me and I can answer them later on. Any questions so far? If none, then I think I'll stop the lecture. Is that okay, guys? Thanks
Sir,
a
can
lot.
we mail you, sir?
Yes, please email me. Yes.
Sir, your email ID, sir, on your IIT Kharagpur.
Yeah.
Okay.
So, Bibhu Datta Sahoo sir, thank you very much. You have delivered 2 very valuable talks yesterday and today. I convey my gratitude from Gauhati University side.
Thank you.